you're coming for a second tutorial. Um, I'll go through for this one. I'll go through like um not so much of what Grasshopper is anymore, but more like I'll go through like the workflow of like writing your own Grasshopper script, especially in like in Kangaroo to do your simulations for exercise 4. And uh I'll explain a bit the difference between exercise 3 and exercise 4 and sort of like ways to go about the thing. Okay. So start with talking about this on the screen now in the iterative versus direct solution. So what y'all have been doing for exercise 3 is that y'all took a solid piece, right, that y'all model out in physical, either physical or through getting the point from a video or whatever. Y'all directly model out something into Rhino itself. Even if you do it through Grasshopper, you're directly modeling it because you know where these points are going to be, right? So you know how the points are going to be. You control the loft yourself, and then you control how the loft. You control the curves yourself. And you control how these curves contribute to the loft, but on your own like agency, and that's a direct modeling solution. And for that's for exercise 3. So exercise 3 is about being able to control things in your own way and still result in organic and like a form finding exercise. Exercise 4 is about iterative solution. So it's about finding a form not from things that you can directly control, but from variables that you can control that influence the behavior of your model. And from influencing the behavior of your model can grow, it can shrink, it can bounce around, everything, right? So, uh, in computational modeling, in like computational like in computation in general, iterative means that if you don't have a solution to the answer, you can iterate it over and over. So say for example, you do 100 iterations, and at the first iteration, you solve a little bit. And then the next iteration, from the result of the first iteration, you solve a little bit more. And then every iterative solution, you get closer and closer to what the final answer is, right? So for example, if let's say like it starts to rain and I want to know where it's gonna flood, there's no way for me to directly get the answer and directly have a formula or solution to tell me, okay, it's gonna rain at 3 p.m. today and it's gonna flood in City Hall. There's no way to know that for sure with a single algorithm or single formula. And that's where iterative solutions come in, where it's sort of like your simulation, where you simulate the rainfall, and every iteration, the rainfall is simulated as like a particle dropping lower by 1 second's worth of fall, or like 1 second's worth of like runoff or flooding. So for example, for that situation, maybe every iteration is 1 second. But this is something that you can control as well, how long each iteration takes. So that can improve the resolution of your solution. But at the same time, it will be more computationally intensive, right? So no need to know too much about that. That's just an introduction of what the different processes are. So uh, that's what it is for iterative. And iterative solution is what you'll be doing for exercise 4. And that's why you'll be doing experiments in a physical experiment and also trying to recreate the experiment in Grasshopper, right? So one easy way to go about exercise 4 uh is to try and think of what experiment can be recreated in Grasshopper in the first place, or that you can sort of see a way to recreate in Grasshopper, right? Instead of you create an experiment in physical and then it becomes too complex to simulate in a 3 week, like in the span of 3 weeks for this exercise. Right. So don't go too all out for your experiment. Try to keep it reasonably complex, but not too complex either. Okay. So if you open Grasshopper, your plugins will end mostly around here at Kangaroo. And these tabs here, these are all the basic components of Grasshopper. It's kind of like your basic components of Rhino, where you have like all these curve tools, you have solid tools, you have subdivision tools, and all these. But these are still quite basic, and it do a lot of like giving thicknesses to your objects. These may be very computationally intensive components, and that's where plugins can come in to help you make this process a lot smoother and help you to compute things a lot more efficiently and help you do your experiment better. So, or like you can, some plugins can just do your experiment entirely for you because the plugins are directed at that specific topic, right? So I'm gonna go through a few generic plugins for today because I'm not sure what experiment you are doing exactly, but I feel like these plugins, everyone should be using them because these are not about the experiment, but about generating the form from your experiment, which everyone has to do in the end, right? So if I go into Rhino here and I create like just a curve like this, right? Just any curve. This curve is flat, and I can't. There's even if this is up here, this I pull this up here, this one, yeah, I pull it down even more. Even though it's a curve in 3D space, but it's not a pipe. Like if I do pipe, sure I can get like a pipe like this, and then from this I get my um three-dimensional curve. But this is creating a pipe firstly in NURBS, which is it's good, but it's not the best for when you do it working with organic geometry. And also, these pipes, you can't really chain too many of them together. For example, if I have this curve and I duplicate it over to the side like this, so now if I'm going to top view, let's just say I want this curve to be here, I want it to intersect with the other curve like this. I go back to perspective view, so now I see the curve is like this, right? If I pipe these two together, you know, okay, it looks all right, but these pipes are not intersecting each other. I can Boolean union them. So I can just type in Boolean union. I choose to assemble these two together, and they do join together. But it still looks like, if I go into render view, it still looks like just two curves that are pseudo intersecting each other, right? And the more of these curves you have, the more computationally intensive it is to give them thickness using conventional Rhino methods. So I'm going to teach you all a way to give these things thickness and also from a single surface. So for example, if I have a surface like this, and I think uh, for those in my unit, I think a lot for exercise 3, y'all will heard this plugin already called Dendro. It's the one that we use to give your surfaces thickness a lot easier than extruding or like trying to offset the surface, right? So you look at the surface and for the sake of simplicity, let's use a flat surface. But remember in exercise 3, a lot of the surfaces are like self-intersecting and it's very hard for you to extrude it nicely. Or like when you extrude it, then suddenly it stops working or like it has gaps in here and there and everything. Yeah, so what Dendro does is that it's a voxelization software. So what it'll do is it will try to place voxels, which are little cubes. Like if a pixel is a 2D square, then a voxel is just a 3D like representation of that thing. So this is a voxel, just like Minecraft. Trying to set a different color. Right? So this is one voxel. And what Dendro will try to do is that you create a voxel at the size that you specify, and you try to place them. You try to what is this? I'm trying to create a clip. Sorry, let me turn off some keyboard shortcuts. Okay. What I try to do, try to place these voxels all along here, along the entire length of the surface. And once it's done with that, then you turn this voxel into a dendro volume, which is just a fancy thing that they made up to give a name to this new spatial context, right? So these are all going to be into Dendro. It's going to be all voxels and all cubes like this across the entire of the surface. And if it's like a curve like this, for example, this is a flat surface, but if you're talking about curves, you're gonna do the same thing. You're gonna march along the curve and try to fit a voxel along there. And then now you realize, oh, this voxel now is deviating away from the curve already. So it's gonna delete this voxel. This one as well, you're gonna delete that voxel. But for example, let's say this one is over here and this is over here. And they realize, oh, the curve is intersecting with this voxel. So you're going to try and keep this voxel and say this voxel is part of the curve, right? And depending on your radius settings and the size of your voxels, this you create a volume proportionally. So if this is the current setting that we use, then our volume is going to be this thick or this big around the curve, right? So let me space first. So that's what Dendro does. Another plugin, oops, another plugin that will be very good is called Pufferfish. So, Pufferfish, what it does, it has all these like components, and if you look at the standard Grasshopper components or so, they are all roughly the same. Like you see mesh, there's a whole tab for mesh up here for in the default Grasshopper library as well. And when you look at curves, there's a whole curve list as well. For domain, there's a whole domain list as well. Under here, under math, there's a whole domain list, and so on and so on. And the thing is that like what I said about Grasshopper components being not exhaustive, like they don't cover the full range of things that you might want to use. So Pufferfish has a lot of these additional like vanilla plus kind of components that help to make your workflow smoother by providing a lot more functions compared to the regular right Grasshopper components, right? So this is not a very specific not a very specific plugin, but I think it's a very useful one as well. And there's also another one called Lunchbox. Oh, this is Ladybug. Lunchbox. Do I not have Lunchbox? Okay, I don't have Lunchbox, but I'll tell you about Lunchbox later. Ladybug is also important. Ladybug is like a site analysis kind of thing. You can use it to do shade benefits. So you're calculating how efficient a shade will be in like blocking out the sun or blocking out the sun rays from hitting a person's eyes, or how efficient it is in keeping an area cool. You can also do incident radiation. So incident radiation is like this is essentially your sunlight analysis or your heat analysis based on the sun. Right. So at certain times you set it like certain times of the day, the sun angle will be this, and when the sun angle is this, you hit your building so and so, your building will heat up so and everything. So this is quite good if you want to do a climatic approach to your geometry, right, or your analysis. But for this specific exercise, I don't think you'll use this. I think pufferfish and dendro are more important. Another one for this exercise is called Kangaroo 2. So this is what I mentioned just now about the iterative solution. Kangaroo 2 is an iterative solver. So it has these components which are different solving different different solvers, I guess, to achieve the iterative solution. So you see all this, there's an on button. There's an on button. Animate is similar to on. And solver is also similar. It just runs without having the on and off button. And what on will do is just it will turn on the simulation. It's just your start stop for the simulation. And there's a reset button where you can reset the simulation back to the original settings and try again with like new settings, or to try again to pause the simulation earlier. Right. And for Kangaroo 2, it comes pre-installed with every Grasshopper. So you don't have to download this. I'll teach you how to download Dendro, Pufferfish, and Lunchbox. Okay. So for Lunchbox is the easiest one. You in Rhino, just type in package manager and go to search for Lunchbox. Yeah, and it will apply here. It'll pop up here. Press install, and you install it. for it to install first. Okay. And you say this up here, changes detected that cannot be completed while Rhino is open, please restart Rhino. So everything that you download through package manager, you have to restart your Rhino afterwards, right? So for now, I'm not going to restart it first because I still have more plugins to download, which is Dendro and Pufferfish. So I'll teach you how to do that now. But like for example, now you look up here, Lunchbox is not going to appear here yet because we haven't restarted our Grasshopper yet. So it's only going to have up to Kangaroo. The rest is stuff that I've downloaded before. So y'all might not have it. So the best way to download plugins for Rhino, for Grasshopper, is go Food for Rhino, right? Food for Rhino, the main page will look like this. You just log in. Okay, I'm gonna show you how to log in because there's a specific thing that you all need to do. Click login and register and let it load. Oh, it just auto logged me in. Okay, never mind. Uh, okay, I think for for you right, when you all log in to Grasshopper and to Food for Rhino and stuff, you come up with the typical like enter your username, enter your password thing. Don't enter your NUS email there. Look below that enter your password and there's a button that says login with Rhino account and then click the login with Rhino account. And from there you can log in with your NUS email and password. Because if you try to log in with just email and password from the very start, you try and log in with a Food for Rhino email and password, which is not what we have. We just want to log in with our Rhino account, which will make things easier. You don't have to create new account and everything. Okay. So once you log in ready, go to the tab and search for Dendro. Okay, click Dendro. And now you get this preview of what the Grasshopper is, and like sort of like some explanation from the creator of the plugin of what it can do, right? So let me go back. Yeah. And if you go to the bottom, or you click here, right, it'll take you to the bottom part here anyways. So it tell you that, oh, this is Dendro version what, Dendro version what, and just download the most updated version. Sometimes the most updated version will be the top one, sometimes it will be the bottom one. You have to read the title to see which is the most updated version and choose and go to the platform. And sometimes they say for Rhino 6 or for Rhino 7, download the latest one. So if it's for Rhino 7, usually it works for Rhino 8 as well, so don't worry. So just click download here and you download to here. So let it download first. And for a lot of plugins, right, especially for plugins that I'm not going to go through today, they have documentation as well. So it's not just you download and then you figure out on your own. A lot of these documentations are within this description here. Sometimes they say on GitHub, sometimes they bring you to a PDF. It depends on the person who wrote the plugin. So instructions on GitHub, if you go to GitHub, uh, right, I click it. Okay. Yeah, so it'll tell you all these instructions. You don't have to do everything. Like I'm going to show you a very simple way to install, which is the same for every Grasshopper plugin, right? All these are just documentation of the technicalities of Dendro, and also some of them will have a like example file hidden within all these like other files as well, right? And find out more details of features and download a working version here. So just follow that and then complete the documentation. Otherwise, just go to this guy, Gary Minas. Type Gary Minas. This guy, Gary Minas Tredekis Grasshopper. I'll send all of this to the year chat later, so you don't have to worry about all these names. But this guy is a really good resource for Grasshopper and Rhino and for rendering as well. He goes through a lot of like different plugins and different methods, which are quite easy to follow along and they are quite intuitive as well, right? So things like he does a lot of rendering nowadays, but last time he used to do a lot of like like these Grasshopper sort of parametric texturing or even form finding or animated attractor fields, stuff like this. Right. Okay, so go back to Dendro. So we downloaded Dendro already, but we got one more file we need to download, and that's pufferfish. We type in pufferfish again in here as well, and download this one, pufferfish. Same thing, click download, you take us to the bottom. See, now this one has a lot of different versions. Like what I said, the bottom may not be the most updated. In fact, this is not even this is not even a Grasshopper file. These are just example files to explain what pufferfish can do, right? Just you have to read and see what is the most updated one. So for this instance, V3 is the most updated one, and we'll just download it here as well. He's going to download it. If you want to play your example file, by all means, download it and go take a look as well. They help to explain the components more intuitively because you can actually try out and play around with it in an environment where the creator already set up the script for you to play around with, right? So you don't have to worry about trying to set it up on your own. Over here, these are our two plugins. I'm going to move it to the desktop. Let's here first. Okay. So go close everything to the desktop. Okay. So we're going to have our two, I'm going to move it on to the side. These are two plugins, Dendro and Pufferfish, right? And you see that it will be a zip file. For uh MacBooks, right? I'm not too sure how the download will be. There's a set of documentation online for downloading Grasshopper plugins for MacBook. Yeah, so installing Grasshopper plugins, and there will be a different this one, Grasshopper for Rhino Packet Mac. They'll have a different set of installation instructions for that. I think you can just follow it. I'll include the link as well. Right. And some plugins only available on Windows, and some will have both Windows and Mac capability. So these ones, Dendro and Pufferfish, have both Windows and Mac, so don't worry. Yeah, you say it down here for Rhino 5 Mac or for Rhino 5 Windows or Rhino 7 Windows, Rhino 7 Mac. Right. Wait to that stop. So for this one, it's a zip file, right? Don't unzip it first. When you download a Grasshopper plugin, it will always come in a zip file, but you need to right click, go to properties, and at the bottom here, at the security section here, this bottom part down here, right? You click unblock. What it does is that it thinks that it's going to be a harmful file, but it's really not. So just unblock it and press apply. So this will allow Rhino later on to read the plugin files better, and so that you can actually load it in correctly. Right. So you unblock already, press OK, and do the same for every file they downloaded. So now I'm going to do it for Pufferfish. Unblock, apply, and press OK. And then now you can extract all. Extract it back to the desktop. So now I have the extractor one here. And extract this one also to the desktop. And this one's here now. Right. So so you see the example files, libraries. This GHA in is gonna be a .gha type file. This is what is actually your plugin, right? And the .dll is your extension to supplement your plugin. So these are the two important files that you need. This one example, you don't really need them. These are just examples to help you understand the plugin better. And documentation is just like a manual for the plugin. And this is very important to read through, right? Especially if it's a new plugin that you never used before and you're having trouble working it out, just use the documentation and very useful to learn. Okay, so now that we have this Dendro file and we also have this pufferfish file, and I'm gonna put it into here. We cannot put it into the same. There we go. We have pufferfish and Dendro. Same thing with pufferfish. This one, the .gha. This is what your solution file is going to be. This is the main file of the plugin. The rest of these, especially, okay, this one also important. These are user objects. So this will supplement your .gha, and this one will also work on their own, but it's better to have these and the .gha. But to simplify things, you don't have to worry. Just think all for this one. I'll teach you how to install. Then we just like a simple drag and drop. Okay. For Dendro, just okay. Actually, not for Dendro. For every plugin you do, you type. You press on the keyboard the Windows button and press R. You bring up the run menu. If not, you can press Windows button, type in run, and you come out with the run thing here also. And type in percent app data percent, right? And press OK. This will bring you to your app data and the roaming file. This is like your for Windows, it's kind of like where your application settings kind of are, kind of something like that. It's like it's like an extension of a program file. I mean, I may be wrong, but that's just my understanding of this. Okay. And go down to where Grasshopper is. So down here, this one. Double click it and then go into here. Right? So from here, what you want to do for Dendro is go into libraries. So libraries is where you're going to keep all of your uh, plugin files at. So usually it's going to be usually going to be an empty file. But once you add more and more plugins, all of them start accumulating here. Then just take Dendro and just drag and drop here. I already have it, so I'm not gonna do it again. But just drag and drop into here. And then your file is gonna appear here. All the examples files are also gonna copy over, but that's okay. It will still dig through the entire of this libraries file to find this one specific file to load your plugin in. And that's okay. Same for pufferfish. But pufferfish, we have to separate it a bit. So remember what I talked about these user objects? So these user objects have to go into a separate file. We can take the Grasshopper assembly file, the .gha, in here under type, say Grasshopper assembly. And this one, we have to drag it into the libraries file of Grasshopper. So just drag it like that. I already have it in there, so I'm not gonna drag it over. But you're going to copy over into here. And then in the Grasshopper, you go back to the Grasshopper file up here and go to user objects. Because these are all Grasshopper user objects, right? They say user files, which are user objects. So you double click the user objects and copy this entire file in as well. So Pufferfish, work in progress, subject components, copy the entire thing here and just let it paste, right? You can create your own user objects also. Not important for this exercise, but like you can create your own components for like frequently used scripts that you don't want to load over and over again. You can just make them into your own component and call upon them whenever you need to use it. Right. So that's one way to get to this file and to install your plugins. And then you restart Rhino and Grasshopper, and it should be loaded into here. Another way to get to that file, instead of doing run percent data percent and going to here, is within Grasshopper, you click on file and go down, special folders. Sorry. Components folder is the library folder. Right? So you click on components, it brings you to libraries. And this is where you put the .gha. And if you go to file, special folders, and user objects, this is where you put your user objects. Right? So this is just the other way to do it. But you have to do this way, you have to open Rhino and Grasshopper and then close Rhino and Grasshopper and then open it back up. Right. So let me just close everything, save everything. Close this, close this. We don't need this anymore now that they are in our Grasshopper thing. We can just delete this also. And then we just open Rhino again. Let it load. Mm. Okay. Once it loaded, then your plugin should be inside here. So Dendro should be here. Where is Lunchbox? Yeah, like maybe it's not. Oh, or so if your thing doesn't seem to load into here, right? One thing you can do for this is under I'll go back to Rhino and you type Grasshopper developer settings and you come up with this, right? So make sure your memory load.jh assemblies is off because this one will tend to cause your files to crash. Then you add a folder and remember the libraries folder we talked about just now. So go back to run %editor and roaming and we go to Grasshopper and libraries, right? So we want to, this is where, this libraries folder is where our plugins are going to be loaded from, right? So you just create a new tab here and in your Windows Explorer, click up here on this thing and select the entire address. Copy it, paste it into here, and press OK. And you open it. You might have to. There we go. It's gonna be here already. Eh? Am I clowning? I think I'm clowning. Okay, never mind. I'll send a way to work around it. I'll figure it out. Settings. If it's not there, you can try this one. This one. Try to reload as well. Reload. Oh, there we go. This doesn't matter. Delete this. Close that. Okay, that's strange. Package manager. Where are you installed to? Okay, never mind. I'll send an update if I figure out how to fix that. But for now, those are not needed. As long as our dendro and pufferfish are loaded, for now that's okay. Because we have kangaroo and dendro and pufferfish already. Okay. So, I'll go into some examples of some scripts that y'all can try out and sort of the approach to setting up your simulation in Kangaroo, right? So I'll go through two of FreeAuto's experiments, the wet threads and also the bubble experiment. These are, I think, relatively simple to compute, and also they produce quite nice forms that I think will be a good approach to this exercise of like using like relatively simple form making, but to produce a very nice and complex form at the same time, right? So for the wet threads, the idea being that you got to break down what all of these, what your experiment is doing. So even though, let's say we look at the wet thread experiment, right? It looks really complex at first glance, right? Like it looks like, oh, there's so much stuff going on. But uh in the realm of like FreeAuto's experiments, they're not super complex if you break it down into its fundamental parts, especially when you try to compute it. So when you talk about a string, you're talking about, we will zoom in into this middle row here. We're talking about a single line, right? And if we have a line and only 2 points on this line, we can imagine the string as a bicycle chain. If the bicycle chain only has one link in it, then it's going to be a rigid chain. It's not going to be able to flex or move, right? So if we introduce more points in between, then our bicycle chain starts to get more flexible, right? And they can start to bend towards one another or anything. And to bend these points to one another, we have to apply a force between these points towards one another. So imagine them as like small little magnets, right? So imagine a string with little magnets all along the chain. And these points will try to attract to one another. And doing this recursively, and we divide a long string into many points and let all these points attract to one another, you allow it to simulate and to converge into a form, right? So, oops, sorry. That's one way to break down a complex geometry or complex system into its constituent parts and to compute all of these in a simpler way, right? So you don't have to take a string and actually like simulate every fiber in the string or something. Just simplify it into its own smaller parts, right? So let's try get setting up to this experiment. So we can do this two ways. Either we start from strings or we start from the anchor points. Let's start from anchor points. We say we have a point here, right? We go to the top view. Say we have a point here, and we say we want another point here. Maybe you want another point here, 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 something like that. Just make maybe more points on this side, right? We select all these points and we put them into a point container like this. So in Grasshopper, we create a point container, right click, set multiple points. And now these points, it's good practice that once you reference something into Grasshopper, right, you should try and hide it, right? Either by selecting everything and type hide, and now it's gone. And now the only thing we are seeing is a Grasshopper preview, right? And this you cannot interact with because it's only a preview in Grasshopper. It's not an actual physical object, right? And if you want to show it again, you can type show. Show will show everything, but let's say we only want to show like this left half that we had here. Type show selected, and we select the item that we want to show, and then we press enter when we're done. And now we only have this left side, right? But for this case, we want to hide everything first. Now we have all these points, right? Then what we can do is go into Kangaroo, and the idea of FreeAutos one is that these points are interconnected to all along to one another. So this point connects to every or the other points. This point connects to every other point. This point connects to every other point, right? And it's a lot to, if you have more and more points, it's very hard to draw all this manually. So what we can do is within Kangaroo, there's a component called, where is it? Interconnect points. So this will very simply help us. You just take the points and put it into the point component of the internet connect points. You see that you immediately draw all these lines for us. Okay, let's make this a bit more fun. Put this aside so it doesn't overlap and stuff. Yeah, so now we have all these points like that. Right? And a good way to know, for example, if you loaded in interconnect points and you're not sure what this component needs to function, you look at the input side. Like I said, this is the input side, this is the output side. So you look at the input side and see what it needs, right? And for now, you can see it needs this points P as a list and the list of points to interconnect, right? And you can see by the symbol as well, that this thing here, this symbol here, this symbol is the point symbol. So you go into parameters, geometry. These are all your geometries and their respective symbols. So it wants a point. So we can't say like, if I have a line somewhere like this, like that, right? I can't throw a line into here. It won't work because what it wants is a point. It won't work on lines. So we have to take our points, put into there. And now we can get it. But we don't know what is it outputting. We can also do the same. We can hover over the output and we see that it has now this, even now it doesn't say what exactly it is, but either you read the list and see that it says line like curve and you can infer that it's a curve, or you look at the symbol again, and for for interconnect, for this component, the interconnect component, it gives this symbol, which is your curve symbol, right? If I hover over here, it had the same symbol as that, right? So now we know these are all curves, right? And now we have set up already this initial stage where we interconnect all of them with straight lines. But like I said about the bicycle chain analogy, is that all these lines are rigid because we have not divided them into different parts, right? So what we want to do is we do a divide curve component, right? Divide a curve into equal length segments. And so we have number of segments and we have the curves that we want to divide it. And we take the output of the interconnections and we put it into the input curves that we want to divide, right? So if we take curves to curves, you see now there are all these points divided along here. So let's say we want, for every string, we want 10 segments. So we have it already. But for this particular experiment, because we're simulating a string, right? And a bicycle chain doesn't have like a string, like if you have a string that's this length here and a string that's this length here, it doesn't mean that this string only has 10 segments and this one only has 10 segments for this extremely long length as well, right? If the smaller this length is, the higher resolution that we can simulate this string as. So if you look at this length here, this is a very long kind of segment and it's going to result in a very rough and jagged string. So if we go into curves and we go into division, we can divide curve by different ways, by equal length, into a set number of segments, or we can divide it by distance or by length as well, right? So we try divide by length, which is, I think, is a better way to do this. So interconnection in curves to curves again, and now it's still not working. And we click here and see input parameter L failed to collect data, right? And we look at L, what is L asking for? L is asking for a number because the symbol also tells us it's a number. And because it says it needs the length of the segment. So right now, my units are in millimeters. If I look at the grid, this is 1 millimeter, right? So I'm not gonna try and set like 20 cm, because 20 cm is gonna be like some long line away from here. It's gonna be like somewhere here, like somewhere here. Like somewhere out there lah. And it's gonna be too long to divide our curves by because these curves are within 78 mm. So that's like within like 8 cm, right? So we look at length of segments. And let's say we want to divide it into 5 mm segments. So we type in 5 in the number slider and plug it in. Now, all these points are evenly spaced now. For example, just earlier on, this one, we'll try to fit it to 5 mm, but it's not, all of them will be fit to 5 mm, but the last one will be whatever's remaining. So for example, if we measure from here also, 5 mm, 5 mm, 5 mm, and then all the way down until there's no more 5 mm to give, then you just give whatever is left. And I think for the sake of this experiment, that's fine. Right. So now we have the lines and we have the division points. But you realize that these are not lines anymore. When you divide a curve in Rhino, for example, I have a sphere and I select the sphere and I type divide and I say, okay, I want it to divide from here and I want how many segments? Let's say I want 10 segments, right? You generate all these points for me. But this curve, if you select the curve, you see that it's still one solid curve. And actually what it does is that it just places points along the curve. It doesn't actually divide it in the way of splitting the curve into many segments, which is the same for this. So in Grasshopper right now, our lines are still long solid lines, and we just have these points that are placed along the line. But these points are not off the line. You get what I mean? Like in this analogy here, we have all these points. We have this one full line, and we also have all these points along the line. But if I take this point and I try to move it here, it doesn't change the shape of the curve because this point is not belonging to the curve. These points are created after the curve, right? So what we want to do is when we have all these points, we can just can do wait, let me see what's the correct workflow for this first. Okay. So with all these points, and we know that these are one segment, one segment, one segment. And in Rhino, a line that is one segment, one segment, one segment, for example, like something like this like this, one segment, one segment, one segment, one segment, like that. This is called a polyline. It's a line made from multiple other lines, right? So in Grasshopper, you just call out polyline and you create this component. And now it says V, vertices. And vertices are just a fancy term to say points. So when you look at a mesh or you look at a polyline, you talk about vertices. If you look at just points by points, you say points. But if you look at the symbol is the exact same symbol. So you can use points for vertices and vice versa. Right? So now we have these lines. Let me turn this off. And we have all these as well. And this will resulting polyline. Right? It's weird. Hmm. Oh, okay. I know what's the problem. Okay. Let's not use divide length. Remember I talked about like the last bit is not, if it's less than 5 mm, it's not going to put another point here. So right now, it's going to think that the curve ends over here instead of over here, right? So so let's troubleshoot that. Okay. So we want it to end all the way here, but this component is not going to allow us to do that. So we can't further reconfigure this component to do it. So let's think of another way to do it. So if we want to divide a curve according to its length, we shouldn't just divide it by a set number. For example, if I have a curve that's let's say I have a curve that is 20 mm long, I can't possibly divide it into 3 mm segments. It will be 3 mm, 3 mm, 3 mm all the way until it hits 18 mm. And the last segment is going to be a 2 mm segment, which is not, it's not going to work because we want it to be 3 mm, right? So let's do this in a different method. So with all these lines, right, we can measure the length of the line, right? So now what I'm gonna try and do is that I know I have a line like this. Let's say I want to divide this into 5 segments, right? And I know the length of this line. Let's set it to a nice number. Let's set it to like 50 mm, right? So now this line is 50 mm long. And I can very explicitly say now, okay, I want to divide them into 5 mm segments. So how many points would I need then? I would need to divide it into 10 segments because 50 divided by 5 is 10, right? So if I divide, and this is the old way of doing it. So if I say I want to divide it into 5 mm segments, if I do it the old way, I try to place it, these 10 segments, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And because we have 10 segments, that means we have 11 points because we have one at the start and one at the end as well, right? So you count points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the number of points that we have is always plus 1 to the number of segments that we want, right? So let's delete away the points first. And what is we say we want to do it in 3 mm, 3 mm, what's the word for it? Segments, right? But we know that we can't possibly fit 3 mm segments nicely into a 50 mm line, but we can approximate. So instead of fitting 3 mm, maybe we can do 2 point blah, 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 right? So let's do 50 divided by 3, 50, and this is some quick math. We do divide 50 divided by 3, and just pull out the answer. So it's this number, 16.6. This is a long, like weird number that we don't like to use. But since we're working in Grasshopper, it's fine. Because when we model it ourselves, it's nicer to use whole numbers because we don't want to type recurring numbers and everything. But if you're using Grasshopper, then it's doing it for us. So no worries, we can just use this anyway, right? So let's say we want to have 3 mm segments. So this is the closest number we get of the number of segments to get us roughly 3 segments, right? So if we try to round this away, so you use a round component to round the number, and we take, let's take the nearest number. So it's going to be 17 segments that are roughly 3 long. So maybe it'll be 2.8, something, right? So what this number is our length, right? And this number here, this 3, represents our segment, our targeted segment length. It's not going to be the actual length, but this is the length of the segment that we want to target, right? And this is the resulting number of segments, right? So now we just decompose our curve division into these few set of parameters, right? So then let's just try to recreate that in Grasshopper now. So if I delete all this and go back to here, see intersection, the lines, and now we have this component called length. What length does is that it measures the length of the curve. So this is going to be this component, right? And it's going to read out all of the lengths of every single curve that we have. And for this one, we have 21 different curves. And so we have 21 different curves here. It says 20 because we start at 0. Because indexes and this always starts at 0, right? 0 is always the first number. So we have all these lengths. And we want to have, let's say we want a segment just now we said to be 5 right? So let's create a slider that says 5. And let's recreate this component again. So now we want our length to divide by our targeted segment length. And we put that component to here and here. And now you see this is our rough number of segments that each curve is supposed to have. So for this first curve over here, let me go down the line one by one. Okay, so for this curve in index number 0, this line curve, it has a length of 40.15 blah, blah, blah mm. And if we want roughly a 5 segment length, we're going to have roughly 8.0 blah, blah, blah segments. But we can't have a 0.03 segment, so we try to round it out. And now we use the nearest number, and these are the number of segments that we need for each curve, right? So now that we have the curve, we have the length, we have the targeted segment length, and we have the number of segments that we want, we can evenly divide this curve into appropriate parts. So let's call back the divide curve component, and we plug in the curves into the curve. Don't plug in these because these outputs, they give you numbers. This is also a number, this is also a number, but what this wants is the curve, right? And now we look at the other components they're asking for. Number of segments, it says 10, but it's going to divide every curve into 10 segments. We don't want that. We want this number that we created, right? That we computed. So we're going to take the output from the nearest number, and then because this is the number of segments that we want, and this is giving us the number of segments that we need. So we just take number of segments to number of segment, and I can see the points are a lot more evenly distributed. If let me accelerate this a bit more. Let's say we do it in 1 length. You can see now it's very evenly distributed, opposed to last one here. If I set this number to a lot more, let's say like 50, you can see along this short length is very dense, and along the long curves is very, very sparse, right? And that's not very good for when we compute it later, because a longer bicycle chain should have more segments. So if we put segments to segments, now we have a very even distribution. And as we set up our simulation to be a bit more robust, right? So let's put this all up here. We don't need that anymore. I can delete all this. If I'm going too fast, please tell me. Try slow down. I'll try explain things slower. I'll also delete this one. Actually, no, I'll keep this one here. So if anything, you can refer, you can understand this a bit better as well, right? So now let's set this back to maybe, let's give it a decimal point. So we have final control. Let's set it to like 2. I think that's a good number. You don't want to set this to be too small, because the more points you have, the harder it is for your computer to compute it. So let's just set it to like 2. This looks like an okay number of points, right? So we go into kangaroo, and now let's create that polyline. So we type polyline again, and same thing, we take our points and we put it into our vertices of the polyline. And now we recreated, we turn off everything else. And now we recreated these lines, but now they are polyline. So even though you can't see it because they are straight, right? But inside here, these are individual segments already because now we created a line consisting of many smaller lines, right? And I just keep it like that. So in Kangaroo, what we can do is let's work backwards from the solver. So we grab out the solver. You can ignore the rest of the solvers. They are just the solvers but fancier. So for this case, let's just do the solver. And we have 5 inputs, right? The goal object. So goal objects are kind of like the targets for your simulation, the stuff that you want the simulation to do. And we have a reset button. We have a threshold, tolerance, and the on and off button. Right? I explained already what reset and on and off does. And so now we just have to worry about goal objects, threshold, and tolerance, right? For the sake of this simulation, you actually don't need to care about threshold or tolerance. Threshold just says when the solver will assume the solution is complete when the average movement is less than this specified value. But for the sake of this, you can ignore these two components. They don't really matter that much. So we just need to worry about goal objects, reset, and on. Okay. So goal objects is your simulation's end goal or the targets they're trying to achieve. So let's give it some goals to achieve. Right. So everything here to the left side of the main component point this unlabeled one, mesh, line, collision, collinearity, angle, and 6 degrees of freedom. These are all your goal objects. This everything to the right of the main component, these are utility things to call out different functions that help you. For example, like our interconnect was called out from utility, this interconnect points over here, right? So let's look at this left side. And we know that we're working with a polyline. So we're not going to look at mesh. We're not going to look at collisions yet. We're not going to look at any of these. We're just going to look at lines first, right? And we know that all these points, all these lines, we want them to have a certain length to it. And we don't want this length to increase or decrease very dramatically. What we can do is take length of line and put it here first. So let's see what it's asking for. We have line, length, and strength, right? This is one way that you can use to create the lines. So from line, we can't just plug polyline to line because polyline is not a line. Polyline is a different type, it's a curve. If you plug polyline to line, it will try to give from the start point all the way to end point, and that will undo basically all this division that we did, right? So we have polyline, and we want to explode it into its smaller points. So let me turn off this divide, and let's explode this polyline into its smaller segments. We call out the explode component. And so we plug in we look at what it's asking for. It's asking for a curve to explode and asking for whether it wanted to recursively decompose until the segments are atomic. You can ignore this one also. This one just means whether you want it to keep exploding the curve until it's really into its constituent curves. Just leave it on true for now, right? You don't have to worry about this. And this one, this symbol here, this is a Boolean symbol. So if you go back to parameters, under primitives, look at Boolean, it's the same symbol. So what Boolean is just a true or false. So we pull out the toggle, this is just a true or false statement. So for now, leaving on true is okay. So you can just leave it there. And then put in curves into curve. And now we have all these segments. So now within here, you can see all these polylines. We have one polyline in each list. We now have the individual segments for each polyline. So if you look at here, if you call it out, you can see linear curve. These are all, even though it's a curve, this is a polyline because we're taking out the from the polyline component. But if we create another one, we plug it into the segments list, now you can see these are the segments for each polyline. So for this linear curve, these are all the individual segments for that curve. And when you look at the next one, 0, 1, 0 is the same as 0, 1. So we see linear curve, and these are all the segments for this curve, and so on and so forth, right? So let's take this explode component and all these lines individually, and we can set them into line like this, right? And if we put this array into our goal objects and we give it a button to tell it whether we want to reset, so go into there. And because we know, okay, so look at reset and on also. So this is asking for booleans. So we got to give it either a button or a toggle. For reset, it will only reset once you give it a true signal. So you don't have to use a toggle. You can just use a button to click it once and then it will give you a true. For example, if I pull this out, it will be false on default. I click it, say true, right? Click it says true. I let go, it says false. For reset, it just needs to give a true input just one time. So we just need a button. For on, it's also asking for a boolean, but it's going to be a constant on or off state. So we just use a toggle. Because a toggle can save whether it stays on or off without me having to put my mouse on it. So we connect this into there. And if we try to turn on the thing now, it says converge. Converge means solution is completed, right? And even if it doesn't say converge, but you see no movement here anyways, you can just assume solution is completed as well, right? Just click through. And even if you spam reset, you see nothing is really happening. That's because even though we have all these lines, but it's like kind of like taking your bicycle chain and just putting it on the table. It's not gonna move up because you haven't told it that these points have to attract to one another, right? So going back to this thing, now we already completed up to this step here, where we take a line and we subdivide it into many, many points. Now we have to add the forces between these points to one another, right? We're the last step ready. So we go back to Kangaroo and we click on goal points. Now, because we want these points to attract to one another, even though they are on the line, they're off the line, but we don't need it. We don't use the line component anymore because these are points now that we're working with. So let me just turn off the explode, turn off the polyline, and you can see now we need to work with points. So we go to goals point, and for this specific one, use magnet snap, right? What? Okay, let me show you what load does. To give an example of what this component does as well. So if we take all the points that we did from just now, so if I turn off the solver real quick, from the divide component, all these points, right? If we loaded these points with a force, let's say the force vector, we want it to be downwards. So let's put a z vector. And because we want it to be downwards, we set it to -1. And we plug it, or we can do number slider. Oops, sorry. Or you can just do panel, type -1 into here, and plug this into there. And that will work as well. So going into force vector. And weighting, for now, you can leave this as it is. Right, we can adjust it later, but we can leave it as it for now. And take the this output and drag into here. But once you drag into here, you realize it deletes away our first line. And you try to reconnect and this away this line. What you can do is you hold shift as you press on this. So if you hold shift, you see the line turns green plus the little like plus button there. You just click on it and drag into there while holding shift and then let go of the mouse. And now it's gonna join in, right? So let's just turn this off first and reset it. So now we have both components into here. Another way, if you don't want to work with all that shifting and everything, just create a merge component. D1, D2 is just your data streams. So put this into your first data stream, this one into the second data stream, and just take the output and put it into your solver. Right, so this will merge the two components together. Just adjust this is neat and tidy. Let's group this together. Okay, so this is our solver. Right, so let me turn off all this preview and turn on the preview of the solver. and let's simulate it. And you realize it just disappears, right? So if I zoom out a lot, you can see that it doesn't just disappear. It just falls down really quickly like that. You can see like in the few frames on the left, if I keep spamming the reset, right? So let's turn down the force factor a bit. So let's say 0.1 instead of 1. Let's reset it. And now you can see it still falls quite fast, but slower already. So let's set it even smaller, 0.01. And now you can see it falls at a more reasonable rate. And I think we can turn this down even lower. There we go. So now you can see if we go back into, if we zoom back into here, and I reset this, you see it starts to fall more reasonably. But you realize this is like now you're just throwing your bicycle chain in the air and letting everything fall down. But we don't want that. Remember in this simulation, in this example, all these points here, these are all anchored down, right? These are not the points that are moving. So how do we do that in Kangaroo? So back to the idea that we're working with points still. So we go to the point goal component and we look through what it has and say, oh, anchor is something that sounds about right. So let's try. So what anchor does is that it will take the points that you give it and make them fix their position in space so they won't move around, right? So let's say we want these original few points here, one here, here, to remain anchored down. So we take these points, we put it into our anchor. Actually, no, let's not do that. Let's let's do it a bit more prudently. So we know that this polyline is what we're going to simulate, right? And we want to anchor down the endpoints of this polyline and let everything in between sag down, right? So let's pull out the endpoint component. So this is a standard Grasshopper component that will extract out for you the endpoints of a line. So we give you the start point and the end point, right? So we want to anchor down both the start and the end. So let's just drag this and drag this in. Same thing, remember to hold down shift. If not, you're going to have to do this again. Hold down shift and drag this both in, right? And take the anchor out as another goal. So just make it little. Put it into this one instead. Right? So now we have 3 goals for it to work. And if we try to reset, and I'll turn off all this again. Now you see, we kind of sag down, but the endpoints are now anchored down, right? And if we increase the weight again, you can see they start to sag even more, right? And one thing we can try do, now that we're only varying the load component, we haven't varied the line component. Remember we say that this component will try to fix the length of this line to try and achieve a certain value so it won't stretch or it won't compress too much. So this is the target length, right? Target length is kind of like I have a line that is this long at first, and target length means by the end of the simulation, I want it to be, like say I want it to be a target length of 20. So it will be this long by the end of simulation, and this is 20 mm long, right? No matter what the length of this line is. So that's a target length. And there's also another component, another input called strength. So strength is kind of like how strongly you want the component to achieve this end goal, right? So for a length of a line, the strength of a length of the line, you can imagine it as the tension of the line, right? So if you think about it just in like verbal form, the strength of a line is the tension, right? So if we take strength and we say, let's create a slider from 0 to 10.0. So 0.1 to 10.0. And right now it's at 10. So let's set it at 10. And we put this in, right? And we go back to perspective view. You can see it starts to sag. And if we reset it and we leave it on first, if we reduce this strength, you see it gets less tense and allowed to sag more and more, right? Alternatively, if we have all these lengths and we say originally all these segment lengths, the target length is 2 mm, right? Let me set this back to 2 mm. and we put that into the length component, right? And we say we want the target length. Let me set this back to 10 so easier to understand. If we say we want to set a target length at the end to 10 mm, that means each of these segments by the end of the simulation will achieve a length of 10 mm. Same thing, the longer your segments, the longer your overall chain is going to be, right? So you're going to have that. Also, if you want to stop it, if you want to stop the experiment here, this is literally how you get catenary curves, like the Sagrada Familia one, because you're applying a gravitational force to a chain, and that's literally a catenary curve. So if you're going for that experiment, this is one way you can do it, right? But for this one, let's try to go a bit further because we're not using forces up and down. We're using forces against one another. This load component is just to visualize what this line segment is doing, right? So we can set this back to 2. Or we can try set it lower than 2. So we say that, okay, our initial line is like a stretched rubber band. So our stretched rubber band has an initial length, but it wants to return to a smaller length. So if we set it to 1, you can see the tension start to increase, right? If I set it back to 2, like that. If I set it to 1, you can see tension starts to increase and it gets more and more taut, right? For purposes of this particular Frey Auto experiment, we can assume the target length to just be the same because these are not elastic strings, these are just thread. And the only thing working on this thread is that the attraction forces between these two. We just want it to be a little bit flexible and a little bit stretchy, but not too much. So we can just set the strength, maybe we can give it like 5 or something, right? Yeah, I think that looks about right. So now, I'm gonna leave this like this for whoever wants to play around with a catenary curve solver later. So I'm gonna copy this, paste it, and bring it down here. I'm gonna group this. I'm gonna right click, disable all of this first, right? So this one, okay, our catenary curve solver. Right? And for this one, let's try and do the wet thread experiment, right? So wait, someone texted me. Oh, okay. You said about the thing, is it? Uh, okay, for yours, right? Turn on the solver, turn on the preview of the solver. So you go into solver here, click it, you right click and turn on the preview. Because I think right now yours is you have your endpoints turned on, you have everything, you have your divide curve turned on. So if I follow what you just have the dots, but you don't have the lines connecting all of them. So if you turn on the preview of the solver, you see the lines start to appear again. Right? Okay, let me continue. Okay, okay. Please ask questions because now that I'm doing it live, y'all can just ask questions. I can help fix any problems as we go also, right? And there's not a lot of us, so I think it's okay. Right. Okay, so let's turn off this simulation first because we don't want to waste our energy solving this and like eat up all the computation power of your computer. So let's delete this component because what we want is really to attract these points towards one another. We don't want it to attract up and down yet. Yeah, we don't want to attract up and down because that's not the goal of this experiment. It's not to simulate gravity. We're trying to simulate like these forces between the points, right? So what we can do within points is we use magnet snap. So snap points together according to proximity. We try and if we have a point like this and a point like this, let's say for now, these points, okay, let me put this over the grid so easy to see. Okay, let's say these are the 2 points that we have, right? So we plug these two into here with points. Radius, our range is the distance at which the snap activates. So for now, these 2 points will not touch each other because let's say our range is let's just set the range of like 5 mm, right? We put this into here. This point, if we take each square here to be 1 mm and we put this point, let's say at the corner of this one, and we count out 5. So if we do a sphere, and we say, sorry, not a sphere, let's do a circle, and we say 5 mm, this is the radius at which the snap will activate. So if you take this point, it's free to move around however you want. As long as the point is within here. If it's out here, it won't have this effect applied. If it's within here, then you start to experience a force towards this circle, towards this inner point, proportional to the range away from this. So it's like a magnet lah. So the further away from the magnet, the weaker the force is. The closer to the magnet, the stronger and stronger the force gets, right? It's like gravity also, right? So that's how magnet snap works. And the eventual goal for this is for these 2 points to converge into a single point, right? And overlap one another and stuff. But for this case, it's okay if it converges, we just let it be, right? So we have the strength. Strength again is like how strong you want this magnet force field to be. Range is how big you want this range to be. So if I set a bigger range, it's just going to expand in range so that, say, every point here, it won't be affected, but every point inside will be affected, right? So let me delete this, and let's take points again. So these points, let's take it from the divide curve component, because that's where we got all these points originating from. And let's take it and put it into points, right? And for this particular one, because now you see we have individual grafted lists, right? If I simplify this, you see we have a list from list 0 to list 20. And all these points, because they are in separate lists, they will not interact with one another. So all these points along this line here, these are all in one list, all these points in one list, all these points in one list, but they do not interact across the list. Everything you do in Grasshopper, they will only be applied to within the individual list, right? So think of them like different classrooms. Say, all these points belong to one classroom, all these points belong to one classroom, all these points belong to one classroom, right? If you have a teacher giving the class a lesson, you only give the lesson to one class at a time, right? But if you want all the points to listen to your lecture, you have to put them all into the same classroom. So by putting them all into the same classroom, we can do it by flattening it. So we right click and we flatten. And this effectively puts all your points into the same lecture hall. So your one teacher can talk to all the points at the same time, right? So once that's flattened, then that's good to go. So we just take the output, the solver component, not solver, sorry, the output code component, and we plug it into the merge as well. So we add another goal to our solver. And now if we reset this and we try to simulate again, you can see it snaps into one another very quickly. And that's because maybe our strength is too high, right? So let's give it a slider. Same thing, or we can copy over the slider also actually. Let's just say now it's at strength 10, right? So let's set it at 10 first. And if we start to reduce the strength, you see it starts to release its tension a bit, right? If we reset this a bit, you can see it's not as strong as previously, but it's still quite fucking strong. So let's turn down the strength way more. Okay, let's give it more decimal points, and now we can turn down the strength a lot. Right? Okay, let's turn this to 0.001 as a minimum, and let's set a maximum as 1, because we know that like this, we know our upper limit now is like even at 0.1 is still too strong. Actually, we can turn this down to a max at 0.01 even, right? And now it starts to look a lot more like what we're going for. If we give it absolutely no strength at all, right? No strength at all, it goes back to its default state, right? But if we try to give it more and more strength, you can see it starts to snap together more and more, right? And this is the range. So let's try vary the range also. Now that we say, or now we kind of figure out 0.001 in this particular scenario is a pretty good number. Let's try to vary the range. And let's use back this 0 to 10 component. So now we have a range at 5. We delete this. And see, if you delete the range goes back to a very, very small default range. So let's put 5 in again. And let's say, because now okay, let me take away the 5 first. If I draw a circle here at 5 radiuses big, you'll see this is the area of effect of this point. So all these points here, they're trying to get pulled towards this center point. So if we set maybe the radius to be like 2, then for now, these points will not get attracted. But if we go to an earlier one and we say we put it at this point here, this point is going to get attracted. These 2 points also, they might get attracted once they reach within this curve. And once these 2 points come together, these 2 points will also have to come together because the string is going to pull them together. And eventually it will move down the line. And all these points will eventually become within range of this circle, right? So let's set this to a small number. Let's say 1.5. And we plug this in and we see. And we can see the attraction is a bit weaker, but if we reset, you'll see it starts to propagate from the points. It starts to attract here, then it goes down the line and attract more and more. And if we reduce our strength of the line, if we give it less tension, we allow it to attract closer and closer. And it's now like quite achieving what we wanted at first, right? So all these numbers, there's no fixed number that is a good number. It's just based on what you want to play around with and what you want to try and use. So you can just play around with these numbers to try and recreate the eventual outcome of your physical experiment, right? So for example, if I try this in real life and I put strings according to this in real life, and I have a resultant form, I can just adjust these sliders to give me what the resulting form in real life looked like, right? I can increase this range so it starts to attract a lot more. Or a way to get a better resolution, like right now you can see the lines are still very jagged. We can reduce the targeted segment length. And everything you edit from up, okay, so I'm going to teach you a new phrase here. It's called upstream and downstream. Right? So what upstream means, for example, this don't have meaning on its own. They only have meaning when we take reference from a single component. So let's say we take reference from the divide component, right? Everything upstream is everything before the component. Everything downstream is everything after the component. You think of it as a river, right? If I have a house in this river here, at this point of the river, if I shit in the river, only everything downstream gets affected. Everything upstream doesn't get affected, right? So this is what is shitting in the river right now. So to this reference to this point, everything here is upstream, where everything down here is downstream. So when you edit a single component, it's going to shit on everything downstream. So everything downstream is going to be affected, right? So by changing this one component, you won't change anything up here, but you change everything down here, which means everything down here will have to recompute. So that's where it's good practice to not do too many edits, not do too many individual edits. Like for example, like changing this target length, right? That's not a very good practice to do while you have this active. Because every single, even though I want the target length to change from 0.9 to like say 10, right? Every increment according to this slider, so it's because this slider is in increments of 0.1, every increment that I do, it is recomputing everything over and over again. So from 10 to 0.1, that's like 99 increments. So it's gonna increment every time and recompute this whole thing 99 times, which is for a more, as the simulation gets more complex, that's not a very good thing to do, right? So a good practice is whenever you want to make edits to your script, you pause the solver first. And if you want to make edits to a complex script, you should right-click on your Grasshopper workspace, right-click anywhere in the open space, and lock solver. Because Grasshopper itself is also a solver. It is not necessarily an iterative solver, but it is a solver. It's a direct solver. But within direct solvers, you can have iterative solvers also. Or within iterative solvers, you can have direct solvers also. Right? So just right-click and press lock solver. So now, as you see, look at Rhino, right? If I change the segment length, nothing is changing. Because to Grasshopper, it is locked. It's not gonna update it until I finalize and say, okay, I want this to be 1 mm long. Then maybe I say I want this length to be target to be 1 mm as well. And I can make all these edits without having to recompute everything. And then only when I'm finished making all these edits, I right click and unlock the solver to recompute everything at once, which is more efficient than if you make one edit here and then it tries to recompute everything at once for every edit that you make, right? So if you make multiple edits, you just want to recompute everything all together. You don't have to do it one by one, right? So now let's say you set this length to 1 and you turn this on and we simulate it again. You see it gets a lot more refined in the way that it solves, and even the way that it animates is a lot more fluid as well, right? One fun thing you can try to do also is within the main part here, you grab a grab component, right? And look at what it's asking for as well. So it's looking for whether you turn on and turn off the strength of the grab component and the range of the grab component, right? So what a grab component does is that right now, all these geometry, they're all Grasshopper previews. You can't interact with them. You can't move them around. But for Kangaroo specifically, they have an interactive feature, which is this grab component, right? So let me just toggle it on first and set the Boolean toggle to true and plug this in there. And I take the goals and put it into there. And let me reset the simulation. And now, if I were to grab onto this point, you can see now I can start dragging it around. And I can start manipulating my shape to however I want. For example, if I say I manipulated it in real life, I can now start to manipulate this in Rhino and Grasshopper as well. It may not be an exact one-to-one recreation of what you did in real life, but it's an approximation, right? And what this strength does is that it's a strength at which you grab it. So if you have smaller strength, that just means you have like weak fingers kind of thing, or you have stronger strength means you have God grip, right? So range is just the size of your hand, how much you can grab at one time, or like at which range you can grab. So for example, even though I'm not necessarily pressing on a point right now, but if I click this space, you can see I'm grabbing something because let's say the range now is 3. If I create a circle at this point and I type in 3, this is the radius of influence of my cursor at this point. That's why I can start to grab points from there, even though I'm not hovering directly over a point. Right? So this is good if say like you have a lot of like points here and there and you don't want to necessarily grab individual points. You want to just grab in the surrounding area and just grab like that. Right? So this is how you do free autos wet threads. Right? And let me turn this off. And now we have all this, which is very cool and all. Okay, let me try to make it not so strong. Give a bit more of that. And also try unhide all these points. Right now we're only doing in 2 dimension, right? But this particular script that we just did, it can also work in 3 dimension. Because if you look at all these points, all these components, right, you realize that all along we've never constrained any of them to only work in a single plane or a single dimension, right? So, okay, let me turn off the grab because this setting gets annoying. So if I take this initial starting point and I try to bump it up and down, you can see it starts to break the solver a bit, right? Because like what I said, you should always turn off the solver before making any edits, right? So let's say I push this up and down, pull this one up, start to move this around in 3D space, right? And then I reset the solver now. So this is the new structure that we're starting from. So maybe in real life, your experiment is not just on a flat piece of paper, but let's say maybe you have like just so let's say you have this. You have all these points here, and let me flatten these points and bring them onto the paper plane, right? And then you have a second set of points that you attach to a different paper, right? And now we reset this, and this kind of gives you the simulation of like if you were to poke holes into this paper and stick points into there, and stick strings from this paper into that paper and vice versa. And you just stick the strings all the way through these holes, right? And if we turn on the simulation now, yeah, this is what happens. You can see how the strings sort of connect from paper to paper and they kind of cross and intersect and everything. Maybe this is a bit too far, bring this a bit closer. Or if we try to twist the paper a bit, we reset the simulation, right? So this is our new sort of starting point. We can maybe bring this point a bit closer because it's a bit wide. Start again. Bring this even closer. Okay, let's just say this is the resulting one. I think it looks interesting enough. And once we're happy with the final look of it, we turn it off. Right? So okay, so from here, what we want to extract out from here is either we want to extract out the line segment, or we want to extract out the point, right? So if you look at V as a list, solver will always output you three things: the number of iterations it took to get to this final solution, the vertices, your points, all these points here, but you see that all these points are now in a flat list and they're not like, okay, all these points here are now in the same lecture hall. They're not put back into their individual classrooms and they are free to sit around the lecture hall however they want. So I don't know which classroom they belong to. This point here, it does not say that, oh, I belong to this classroom. Maybe it belongs to this classroom, but I don't know that. Right? So we go to outputs instead. And from outputs, if we connect in a panel to read out what the output is giving us, you see it's a whole lot of nothing until we get a whole lot of something, right? So we have all these lines here. And what we can do is, for this specific instance, right, we can join all these lines together. We do join curves and join it together. If we turn off the solver now, we can see we have all these curves. Polyline curve, polyline curve, polyline curve. So now what it does is that, because within here, you get all these points, right? Run this up a bit more. All these lines are within their own classroom. So we don't have to worry about trying to sort them back into their classrooms after we send them for lecture, right? So we can take all these lines within the classroom, and put them into one long polyline curve. Because we can organize them and say, okay, all these lines within the classroom belongs to one single polyline. Instead of saying, if I were to flatten this, then it's trying to say, oh, my entire lecture hall is supposed to fit into a polyline. So you try to make as many polylines as they can from the entire lecture hall, which is not what we want. We want each classroom to be its own polyline, right? So now we have all these individual polylines here, right? But we also see we have all these like unnecessary lists that we have to work with. Doesn't matter. We can just, for now since we put everything back into the classroom already, we can flatten it. Just now we have each individual classroom. Remember, we started out with 21 lines. If we do a panel into here, from 0 all the way to 20, right? And we go back to here, and now we have 0 all the way to 20 as well, right? So now we recreated all the starting polylines already, right? So once we have this, we can go into dendro, and that's where we can start to thicken these lines, right? So for now, these lines are just lines. They don't have a thickness at all to them. But if we go into dendro and we go to the convert tab, we can look at these few things. So what dendro has is a few components: curve to volume, mesh to volume, and points to volume. Sorry, it's taking a bit long. It's already like nearly 12. If you need to go, please do go. This is all recorded, so I send the recording to there also. But if you can stay, please do. I think we're gonna try finish up this one experiment first, and the next experiment is a lot faster lah. So let me just explain this real quick. So for dendro, you have three methods of creating volumes. Create volumes from a curve, you create volumes from the mesh, or you can create volumes from individual points, right? So if I create a point here like this, I have many points like this, and I put them all into one geometry. So I put them all to one. Okay, geometry is like a generic container. If you know what you're doing, not if you know what your components are, you can put them into specific containers. But if you don't know what they are represented by, you can put them into a geometry container because it will accept anything. So it's a bit more easy to work with, right? So you take the points, put them into B points. But you see, it's still orange. So you say input parameter R field to collect data and S field to collect data. So look at R and look at S. R asks for radius. Remember earlier on we talked about the radius of the voxels and around the points of the putting voxels around the points. So like how if you have a voxel like this, it's trying to put, say if our radius is 3, do a sphere because now we have 3 space. If our radius is 3, this is our radius around this point. And if you look at the ghosted view, right? Wireframe view. Within this sphere, you're going to try fit voxels within this radius. So you're going to try fit up to here, maybe this one as well, this one down here, and try to voxelize this sphere into a shape that we can recognize like that, right? So and then copy it around and around, so like this, like that, and then maybe have something like that. So this will be our approximated sphere in a voxelized form. Right? So let's delete that. And let's just move this point back there. So we have our 5 points, set multiple points, and like that. Okay. And now we need a radius. So let's say we want our radius to be, for now let's set it at 3, apply into there. And we need to create a dendro setting. So dendro setting, you go under convert and create settings. And this will create our dendro settings. We don't plug this in straight away first. Let's look through what it's asking for. For the voxel size, like I explained just now, the bandwidth, the ISO value, and adaptivity. For the sake of this, you don't have to care about this bottom 3. Just care about the voxel size, right? So for example, if I have all these voxels just now, right? This length here, this edge of the voxel, that's your voxel size. So the bigger your voxels, the bigger the size of the voxel, the less that the software has to try and fit all these voxels into there. If your voxels are very small, say they're like this size, right? Yeah, delete all this so you can see. Right? If your voxel is this small, to achieve the same distance out to here, if you can see, it's gonna take you so many. Whoa, that's weird. Okay, wait. It's gonna take you so many voxels just to achieve the same distance, right? And because we're working with 3D space, so every reduction of like 1 unit of voxel size, you're going to effectively cube the number of voxels that you have to fill in the same space, right? Because these are cubic. So let's say this voxel size, I want it to be something not too small, but something that is big enough to approximate the size with a good resolution, right? So if we plug in 3 to 3 and we plug in our setting to setting, you can see it's still orange because since radius must be at least 33% larger than voxel size, right? So if we set our, either we can increase the radius or we can reduce the voxel size. And let's say we want our radius to stay fixed like that, right? So if I select all these points, I put it back into here. I want my radius to be the same. So let's reduce the voxel size slowly, right? We reduce it until we see a form starts to appear. There we go. But you can see it's very rough because our voxels are still very big. So the smaller we go, the more and more it becomes spherical until it gets very small voxel size, which is a bit scary, right? So I think just go for a shape that like approximates it enough that when you make your model production, like say this is a 3 mm sphere in real life. You don't need to be so precise because a 3 mm sphere is going to look like that. You're not going to be able to tell how jagged the edges are because it just looks small. Once you 3D print it, you can't tell anyways, right? But the cool thing about Dendro is that these are all individual spheres, yes. But if I start to move them together, you can see they start to join together and start to like like reverse cellular division kind of thing. They start to smooth themselves out like that. Like if I move it here, if I move this one to here as well, you can see it starts to join, it starts to smooth out like this, right? Even if you do it in 3D space also, you will start to move smooth like this. I create one maybe down here like this, and I click set points. You see it creates a point like this, right? A whole mess like this. So this is one very good way from individual points that don't have a volume yet to immediately give a volume to these points, right? To give a physical dimension to them. So now that you have a dendro volume, but dendro volume, even though it's being rendered, it's not a grasshopper or rhino kind of geometry. What we need to do after this is to convert it from a volume back into a mesh, right? So we take the volume and we plug it into what it's asking for. So asking for V and S. V is asking for volume. The S asking for the settings again. So we plug the settings back into here. We plug the volume back into here. Now you can see it creates this mesh, right? And this is what we can bake. We bake it into our solids. And if I turn off the preview, now we have a physical object that we can work with in Grasshopper, or with Rhino, sorry. And it's a bit rough, but you can set this voxel size even smaller to achieve a smoother thing. Another way is that if, for example, let's say I have a very big radius, right? I can increase the radius, you can see it starts to, if I increase the radius with a better resolution, if from individual spheres, they start to connect and join to one another, they start to melt together, they start to smooth each other out. But let's say I don't want it to be so lumpy, right? Right now it's still a bit lumpy. I can go to filters, smooth volume. I connect volume to volume. And now I have a smoothing function. Let me disconnect the meshing function because I don't want it to mesh yet. And I turn off the original V points. So now I have a very, very smooth volume. And I can change the width of the smoothing, say 1 to 10. It starts at 1. And if I increase the width of the smoothing, you can see it tries to apply the smoothing to a wider and wider section until it starts to decompose into a very weird shape. So this one, for most purposes, can keep it as 1 or 2, right? And the type of smoothing that it does. So for this one, either you leave it as the original one, or I like to set it to Gaussian. So just set it to number 0, right? So it tries to smooth it in a very organic way. And you can change the number of iterations that you try to smooth it. Right? So now it's only smoothing it one time. But let's say I want it to smooth another time. Instead of creating another component and plugging it in, and then plugging it in, and then plugging it in again, what I can do is just, for this one, I can just give it a number. I say I want to do it 5 times. If you have a number slider that says 5, and just plug it in. So for example, now if I do it only one time, it's going to look the same. And then if I increase the iterations, you can see it tries to smooth it more and more until it slowly disappears. Right? So think of it as like you have an object and you are sending away the object. So the more you send away your object, the more material you take away from it until it disappears. So try not to set this to too high. Once or twice is good enough for this as well. Right? You can take your output volume, connect it to your meshing, and now we have a new volume that is a lot smoother and a lot more for my purposes, a lot more workable. For say I want to have a smoother volume. But if you want a more jagged volume, you can just take the original volume. That'll be fine as well. But if you don't want it to look like one sphere, one sphere, one sphere, if you're working with points, you can always smooth it out into a more organic shape, right? So let's apply this to the strings that we have right now, right? Exact same thing if we have a mesh or curve. You can see the inputs are the same: curve, radius, settings. For mesh, you don't have to set a radius anymore. It's just the mesh. So mesh and settings, right? So let's ignore mesh for now, since we're working with curves, right? So we just take the curve component and we plug curve to curve, right? It's still going to be orange because right now we only plug in this component. We still have to plug in this, and everything else. So let's make a copy of it. Group it, say dendro example, right? I'm going to put this here, and I'm also going to disable this. If you download the file later, you can highlight everything, right click enable, and you can start to play with it again. But to save the computation, I'm gonna disable it so that when you open the file, you don't lag that badly. So let's create a curve and say we want the radius to be, let's set it to the same, 3.7, and set the settings to be the same. And now we get this shape immediately. And it's very thick, so maybe we reduce the radius a bit until we get something we like that. Okay. And to visualize it better, let's do the same thing. Let's try to volume to mesh and connect our components in as well. And now we can see this is the resulting form. If we bake this, the solids component, it's gonna look a bit degenerate. But that's because our mesh right now is inside out. So if you look at it and you realize like it looks very funky or look like you're looking at the inside of the mesh, select the mesh that you're working with and just type flip. Right, type flip. Flip the direction of the mesh. So now you're looking at the outside. So you're gonna look like that. And you can, because it's a closed mesh, Dendro will always give you a closed mesh because it's coated like that. Then you can just take this and immediately export it as a STL to print. So this will be immediately good to go to 3D print, right? And if say I don't want it to look so uniform all the way, like this looks like just columns add together, it doesn't look organic enough to me, right? Then maybe I can try smooth it. I put volume to volume. The width, let's set it as 1. Let's keep it as 1, sorry. And we delete this away so we can look at what we're working with. And number of smoothing iterations. Let's give it a slider from 1 to 10. And now if we increase the slider, you can see how it starts to smooth more and more, right? Let's say this is good enough for me. Let's set a Gaussian because I like that better. So maybe Gaussian smoothing is too strong. Let's set it like that. Maybe the Gaussian really is too strong. Set it to other ones. Ablation might work better. So now we have that. And set it back to original. Okay, let's say like that. It's good enough for me. Or we can also change the width for smoothing. So from 1, let's increase it to maybe 2. It starts to mess up. Let's not increase to 2. Let's just keep it to 1. Okay, just work with this. This looks, okay, let's just say this is good enough, right? So now we connect our volume to the mat to create back a mesh and disable the preview for this and enable preview for this. And you can see it looks a lot more organic now. It's like it's reducing in radius at certain points, and where there's more lines intersecting one another, it's going to thicken in radius again. Right? So let's take this in the solids. And now you can see comparatively to our previous piece. We flip the previous one as well. You see it's a lot more organic, where it's not just so consistent between the radiuses. Like here, it starts to taper down and everything, but it gets very stretched in. So it's like imagining you're like you're stretching like a slime or something. It starts to get thinner, where it's a lot longer. Right? So there's one way you can work with Dendro, and one way you can give your forms volume very quickly. Right? So let me group this all and say fray auto wet threads. Okay. And now we disable this. Okay. So that's it for the wet threads. Now let's look at another example. Right? If you need to go, feel free to go. I think the basics of what I'm trying to teach is already done. The idea of setting up components in Kangaroo is already done. So this will give you a baseline for setting up I lost my train of thought. For setting up a simulation in Grasshopper to emulate what you do in real life, right? The next one I'm going through is the bubble experiment, which even though it's slightly different in that we're going to simulate a mesh instead of simulating a line, the concept is the same. The idea of looking for what these components are looking for and giving it the components that you need, and the idea of upstream and downstream components, the idea of different strengths and different properties of the components, all of these stay the same. Just that for now, we're working with lines. We're going to use things in the lines tab. For later on, if we work with the mesh, we're going to use things in the mesh tab. It's just kind of like these are just vocabulary that you can use, but the idea of how to put your sentences together has hopefully is already something that you all can understand a bit better now with this example. I'll go through the bubble experiment now so that we can see how that will look like. Okay, so okay, let's create a new part on here. Let's say, okay, let's try and recreate this specific experiment. This one in the top right, right? So, full auto bubble. Okay, let's try and recreate this exact experiment. Right? Put it here. Right? So this experiment is very, oh my god, that's weird. Okay, it's relatively simple in that what it is just it has an outer frame. So this outer frame here, this one here, and it has these two probes that sort of like push against the bubble surface, right? This outer circle here and this circle here, right? Okay, we're looking at this in from an angle, but what it is just a rectangle, and then you have one circle here, right? And then another circle, oops, sorry, and another circle over here. And one of these circles that we're using to push the bubble, he pushes it up. The other one, he pushes it down, right? So this is where we can talk about the iterative versus direct solution, right? Just now I talked about, at the start I talked about iterative versus direct. So this is one example where both iterative and direct can give you an answer, where if I take all this, and because bubbles are just a surface, right? And we worked with surfaces in exercise 3, where we just lofted things. So we just loft it. It looks weird, but if I give it a... Oh, that does look weird, never mind. If I do this instead, patch, you can see it starts to create something like that. And if I take this and I trim away, if I extrude and then I split it by this, I delete this, oops, sorry. And start to see it looks something similar to that, but it doesn't have the same qualities of the solution where these are minimal surfaces, which means that this is a minimum surface area to represent this geometry, which is what bubbles will give you, because bubbles are surfaces in constant tension. So they will try and shrink as much as they can to give you a minimum surface area. Just like how this experiment tries to do with string tension, now we're working with surface tension, right? So this looks a bit off because it slopes in the wrong way, right? So this is the difference between a direct and iterative solver, where direct solvers, if you don't have the exact methods, you're not computing exactly like bubble physics, right? You don't have an algorithm to compute that. So that's where it starts to break down in that it becomes an approximation. But if we do iterative solver, we can get as close as possible to a real solution through stepwise, through small approximations every iteration. But through a very many number of iterations, we can get very close approximation of a real life scenario, right? So let's set up the experiment, okay? So we have, let's say, these two, and we don't need them to be so high or so low first. So let's undo everything back to when they're all in the same plane, right? And for this specific thing, you can do it in Rhino or Grasshopper. I'll show you a way to do it in both. So for Rhino, you can just select all these and type inner surface, and that will create a surface with these two cutouts, right? So let's just imagine that these two are, that this is the probe, where this probe is not pushed up and down into the bubble surface yet. They're just on the bubble surface. This is where we set up for the experiment, right? So that now we have this surface. But if we adjust this in Rhino, if we push this up, it doesn't move the surface alone, because the surface is already created. And Rhino is not an iterative solver. Rhino is a direct solver. So we have this surface and we have the inner rings, we have the outer boundary. Let's set it up in Grasshopper instead. Okay, so the setting up of this initial condition, you can do it in either Rhino or Grasshopper to just get this initial open surface. This is how we did it in Rhino. If you want to do it in Grasshopper, you can do it by, let's set up the conditions first. So let's have 3 geometry containers. Let's say 1 for each of these curves. So we have, let's choose the first one. We set 1 geometry. We label it as boundary. We choose the left circle, set it here, which say left probe. We choose the right circle, we label it here, say right probe. So, oh, then we right click set geometry. Yeah. So now we have all these probes. And just arrange it, and we can hide this away in Rhino already, right? We bring this over here so it's easier to understand. Right. So all these are still planar, right? In Rhino, remember we did the command above. Where is it? I can't find it anymore. But it's the command we did was planar surface, where we took these 3 surfaces, we type planar surface, and it creates this initial surface for us, right? In Grasshopper, it's called boundary surface. Boundary surfaces. So if we take just this and put it there, it just creates a boundary surface along the entire boundary. But that's because we only told it to create around this boundary. So same thing, let's merge. Use the merge component. We put all these together. So now we have all these 3 into 1. And we create a boundary surface from these 3 curves. And we create the same thing that we created in Rhino just now. So now we have just this volume that's outside of all these curves. Right? Let's turn this preview off. And now we have a surface, but we need to work with a mesh. So let's turn this surface into a mesh instead, right? So what we can do is we do mesh that and put it into there. Right, so that's going to give you a very weird looking mesh. And if we try to simulate this, like remember the string example where each string is one long chain, is one, not one long chain, each string is one single chain until we subdivide it, right? So a mesh is exactly the same. Every mesh edge that you see here, this is one long and rigid edge. This will not bend. If you want it to bend, we can make this circle bend because you can see it's made of many, many small edges over here. But this long edge here, this will stay rigid because it is one long chain. This is the bicycle chain, this is the metal beam, right? So what we can do is change the mesh settings. So if you go into the mesh tab and we go to utility, go into triangulation, we can change the mesh, utility, we can go into the settings where the mesh wrap comes from here. Next to the mesh wrap, you have the settings here, bracket custom, speed, or quality. By default, it comes with the speed setting. So it tries to make a very simple mesh to make the mesh very quickly. But because simple meshes do not represent our bubble surface very well, let's try and create a more refined mesh. So from here, either you create custom quality where you make a smooth mesh, where it just tries to create more lines, which is not exactly what we want. What we can do instead is try to remesh it, right? So let's do a triangular remesh. What triangular remesh will do is that we take this whole mesh surface, and if I plug it into geometry, you can see now it tries to fit the mesh into all these equally spaced out triangles, where all these are individual edges, and they can simulate a lot better now that all these edges are shorter, similar to what we did here, where we divide the edge into more consistent parts, and also they are smaller and there's many, many of them, right? So if you look at the individual inputs, we have target, you can ignore this one. We have sharp, we have features, length, and iterations. For this purpose, you can ignore everything except for sharp and for length, right? So sharp will preserve whether you want it to preserve the sharp features. And this is a Boolean. If you look at the symbol, it's asking for a Boolean. So this means we need to give it a toggle, right? So sharp, say we want it to be false for now, maybe, which means if this corner is a sharp corner, it will not try and prioritize to make this corner a sharp corner. So what it could have done is very easily make the edge this edge here instead, and this part and this bottom right triangle here will not have existed, right? But for this experiment, because we have a preset boundary that we need to adhere to, let's turn the sharp corners on so that we can preserve all those features, right? And now we look at length as well. So what this is asking for is a number. So we look at a symbol and we go back to parameters. We look at primitive, it's asking for a number. You look at the symbol here and the symbol here, the same thing. And number means we can use a number slider for it. So let's create a number slider. And so this is asking us to give the target edge length, which is the length of all these edges here. So for now, it's just going to try and create a mesh that's decently spaced out. But let's say we want it to be a more refined mesh, right? What we can do is that now these edge lengths are 5 mm wide. Say if we want it to be a more refined mesh, we can set the target edge length to be even smaller than 5 mm. So if we give it a slider from 1 to 0.0 to, let's say, 5.0, our starting value. If starting value is 5, let's try give it maybe like 2 or something, and we plug that into the length. You can see now the mesh becomes a lot more refined. It's going to take a lot longer to compute, right? To turn on this this profiler to tell you how long it took to compute, right? Go to File, Preferences, and go to Widgets. Under Widgets, you scroll down. You can't use your scroll wheel for this for some reason. You have to click the right side here to scroll. You scroll down, then show profiler widget. See, if I turn it off, it turn off the number here. If I turn it on, it will show you how long this specific component took to compute, right? So each of this will take, if it takes shorter than like 10 or 20 milliseconds, it won't show. But if it starts to get more intense and more like it takes longer to compute, then it will start to show lah, right? So this specific one took 144 milliseconds. So the longer the edge length, you can see it's simpler to compute because it doesn't need to fit so many triangles in. But we try to refine it more and more, you can see the number, the time taken starts to get more and more, right? So just set this to a level which is appropriate for your own computer. So you can try. Honestly, I think this original surface is good enough. Like if you don't even add any length into here, this surface is honestly good enough and is a good starting point. If you want it to be, you want the simulation to be even more, to have even more resolution, you can by all means change the length. But for now, let's just keep it at the original. Okay. So we have this mesh and we have our original boundary conditions, right? These boundary conditions, honestly, we can just turn it off already. Now that we have the mesh, that's all we need to work on for this example, right? So let me teach you a bit of mesh terminology. Okay, so in a mesh, there are a few things. There's the vertices, right? Okay, so let me put this into here. There are vertices, there are faces, and there are edges. And there's also the normals to the mesh, and there's the color of the mesh, right? So these are the 5 properties of a mesh. There are more also, but for now, these are what we sort of need to know. For this exact experiment, we don't need to care about normals or color. We don't even need to care about faces also. Sorry, we don't need to care about faces, but we need to care about edges, right? So we just keep let's just put this to here. These are the 2 that we have to work on for this particular example. So what is a vertex and what's an edge? But like what I said before, vertex is the individual points. So these points over here, this center point over here, the point over here, if I visualize it for you, the mesh, right? So if I turn this on, you can see these points here, these are all the vertices of a mesh. And if I do edge, I extract out the edges, these are all the edges of a mesh, right? So these together, we tell the mesh how these vertices are connected to one another. And the boundaries of these edges, you define for you each face of a mesh. right? These are good to know stuff. You don't have to use it for this exercise, but if you want to go more into computational geometry, these are very important things to understand. So mesh edges faces normal, which is the angle of the mesh. So for now, the mesh is a flat mesh. So all the normals are pointing. Normal is like the perpendicular vector to a point on the mesh, right? And they usually exist at the vertex. So that's how a computer will reconstruct a mesh from numbers to tell you that okay, this vertex is at this angle and this face is at that angle and blah 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 blah, right? So, but for this example, we just need to care about vertices and the edges. So you can see here we have three different types of edges as well: the naked edges, interior edges, and non-manifold edges, right? So non-manifold edges, we don't have to worry about for now. What we need to worry about is naked edges and interior edges, right? So if I visualize it for you, naked edges are the edges that do not have do not have mesh faces adjacent to them, right? So this essentially are our boundary edges, right? Even though it's less resolution than the original boundary edges, like for example, the original boundaries are this curve here, but now that we are working with a mesh, they are working with straight lines. So we turn it into a discrete curve, right? And they're all individual lines, if you can see from here, right? So these are naked edges, and internal edges are the edges within here, right? So this is very important for this experiment because what we're simulating, what we're only gonna care about is the internal edges. Since the boundaries are already set for us, we're not gonna have to worry about them. In the same okay, we still worry about that, but not in the same way that we worry about the internal edges, right? And same thing for vertices. Even though the vertices right now is a collection of all the vertices, but if I turn on naked vertices, this is also a kangaroo utility. We can go into the mesh utility and click on naked vertices to create this component here. And if you plug this, we ask see what you're looking for. It says looking for a mesh. So we take our mesh and we put into here. It's gonna show us all these different vertices, right? So the first two, closed index and naked index, don't have to necessarily worry too much about it for now. Index just means which, for example, if it is, right? Index is this number here. This is which number your point is. So for example, let's say clove index, let's say, if I plug this into here, this numbers here, these are the indexes of the points that are clothed. Clothed is I think it's just their fancy way of saying like it's not the naked edges lah. So a naked point, similar to a naked edge, where is the boundary lines. The naked points are the points on the boundary, and the clothed points are the points within the boundary. Right? So that's just one way of managing your data. So let's delete all this first, and let's just keep this tree here. These are important. We'll need to have the edges. This one, because it only tells us all the vertices, but it doesn't distinguish between boundary and internal vertices. So let's get rid of this one as well. And let's keep this component naked vertices because it tells us what's the internal one and what's the external ones, which are important for this, right? So let's set up the simulation. Okay, so if we go back here and we click on solver, and same thing, we work backwards from the solver, right? So we need a goal and we reset. So reset, we give it a button, and we give it a button here. Toggle for the on and off. And let's set it as false for now because we don't want it to unnecessarily run. And let's just group this together so we have this one component. Okay. Let's create our merge component also because we know that we're working with multiple goals. So let's set this up first. Right? So what do we have to set up for a mesh simulation? Right? Because we know it's a mesh, so we don't work with lines anymore. If we are working with mesh, the edges, and the mesh vertices, we can work purely in a mesh and the points. We can also work with this, but there's a way to work with mesh easier. Instead of interpreting this as individual lines, we can just, there's a component created for us that we set the edge length instead of the line length. So this will collectively set all the edges here to be a length that you want, which is a bit more convenient, lah. Right? So let's say we want to talk about bubble tension and we want to talk about the boundary surfaces, right? So if we go back to the same example here, tension being the strength of the line, and the boundary surfaces back then was our boundary points, but now we're using boundary surfaces, right? But we can use the same thing. We can use the anchor still, because this boundary surface is also represented by a list of boundary points, right? So let's work with mesh edges and work with boundary points. So we take, look at what it's asking for, mesh, length factor, and the strength. So mesh to mesh, and let's move this down so we've got space over here. Right? Length factor is what I'm asking for is a target edge length as a multiple of the current length and not as a discrete number. So that, like how previously we were saying we want it to be a specific number, this one we're just saying we want it to be a multiple of our existing number, right? Or the existing mesh length, right? So if you want it to be tighter or you want to give it more tension, you give it a number smaller than 1. You want it to be a longer length, you give it a number more than 1. For a bubble, because a bubble tries to minimize the surface and tries to be as small as possible, let's give it a number smaller than 1. So let's create a slider from 0.1 all the way to 1. And let's set it for now to be 0.9, right? And our strength, same thing, is strength just means like how strongly you want this to be affected, how strongly you want this to be applied. So this is essentially your strength of your mesh will be your surface tension, right? Then we put this goal into the first goal that we want to work with. And then now we want to anchor down these points. Okay, so let me show you the simulation real quick. So if I turn off the preview of this, I turn off the previews of all these, we just talk about this one here. Okay, for this one, it will be good practice because in objects, it will not show you the mesh anymore. Because now it's working with edge lengths. So it's going to show you the edges instead. But we want to reconstruct a mesh from this. So let's go to main, click on show. And from show, what you can do is that what this component does is that it will forcefully show the geometry that you are inputting when it's simulating. So for example, we say we want to show the mesh again, like this mesh here. We take the mesh, go into show. Because it's a generic geometry container, you don't have to worry too much about what you're putting in, right? And then we put this into our one of the objectives for our solver as well, right? So like that. And now if we turn off all these and we keep our mesh here off, you realize that now we have our mesh showing again once we preview our solver. And if you look down here, if you go into the panel, you see in the list number 0, there's a mesh now, right? So that's good. That's good for us. Because at the end of the day, what we want to extract is the mesh. We don't want to extract the points or the lines. We just want the mesh itself, right? So if I reset the simulation and I turn it on, you can see it just shrinks because this our length factor. That's just all we're setting right now. Give it a bit more deep decimal points. You can see we're just varying the length of the edges, but we're not setting it to be like, say, okay, so we're not telling you that, oh, these edges have to remain in this specific angle. So if I mess around with this and like bundle it up a lot, right? I just like push it in and out. You can start to see it's like you're taking a piece of tissue and then you're just shaking it around. It starts to overlap and touch and like let's like press into each other, right? So let's set it back to underneath 1. And now let's anchor down the edges, right? So if we have naked points as we saw previously, let me turn on the simulation. The naked point previously, let's anchor it down. So we use the anchor component again from naked points into the points. And we set our target. We don't have to worry about the rest of the strength or so. You can just ignore this for now. The anchor point is usually set up good to go out of the box, right? So we take the anchor and we put it into one of the goals. Now that if we turn on the simulation again, no matter what we change our edge factor to, you can see the mesh starts to rearrange itself as it tries to like achieve a more achieve the edge factor that we are asking it to achieve. But if you look at it in 3D, it doesn't move. It doesn't move in and out, up and down or anything. But that's because we fixed the boundaries. So it's only gonna simulate within here. Not only gonna simulate, but the edges won't move from these boundary points anymore. So these are like it's taking we have a surface and then we staple it down at all these points. So it's not gonna move anymore, right? But now you realize that these boundaries and all these are they're all flat with one another. And by creating this boundary, right, if we say we want to move these surfaces up, right, if we take this initial right probe and we push it up, you can see it breaks the simulation. Because now this is no longer in the same plane as the rest of the surfaces. So it's not able to create this surface boundary anymore, right? What you can do instead is, actually, I'm not sure if this works. Let me try patch. Let me try this. Okay, yeah, it doesn't work. I try and move it up and down. It looks somewhat similar, but similar to just now when we did it in Rhino by itself. You can see it's kind of bending in the wrong way and everything. So let's not use patch. Okay, let's delete this. Turn off the solver because it's a bit annoying. Right. So what we can do is, if we know that these are gonna be our edges. Oh, actually, wait. Okay, there's a few ways you can go about it. Yeah, I think, okay, so in Grasshopper, there are a million and one ways to go about anything. It's just what you're comfortable with and what you know how to do, right? So right now, this method that we have is going to put all these edges, all these naked points into one single edge, right? But if we say, we can re-reference these points to take only the points here and the points here, and we can set the target. So remember this target thing where we can pull the anchor to? So if we set a target to something like up here and set this target to something like down here, then we can start to adjust these points accordingly, right? So that's one we can try. So let's try to set it up. This will be a bit more complex, but after this, I'll go through a simpler way that you can try and do this that involves more of this part here instead. So now there's ways to do it within the simulation. There's also ways to do it within the simulation setup. Okay. So let's talk about the within the simulation first. So if you look at this container, you can see that these are all the points. But like what I said about the lecture hall, now all these points are in the same LT. They are not in individual classrooms. Let's take this all these as individual classrooms. So your left probe with a boundary and the right probe. These are our three classrooms that we're going to work with, right? So let's reference in, or not reference in, but let's say we have, okay, no, they can reference in as well. So let's reference in the left probe and right probe that we want it to target. So the offset right probe, let's put it here. Let's label it as offset right probe. And the left one, let's say offset left probe. And we set it into here, right? So now we have the offset one and the offset right one and offset left one. And let's move it back to here, right? So what we can do now is the geometry, from the geometry here, we need to identify back these points. We need to somehow identify characteristics of these points that let us group these together, put them in one classroom, group this together, put in one classroom, right? What we can do is that since we know that these points fall on this curve, right? We can do a component called point closest to curve. So we go to curve closest point, sorry. Find the closest point on a curve, right? So take this, and from the whole lecture theater, we give announcement. We say, okay, all the points that are closest to this curve, please stand up and leave the room now. So we take this and we put into the points. So for this component, it will ask for a point to project onto the curve and the curve to project to. This just means the points you want to analyze and the curve you want to analyze, right? So let's do the right side first. Let's do a right side probe and put into the curve component, right? And you create all these points up here. Don't have to worry about all these points here. What we worry about is the distance, right? So this is not really telling the points to stand up and get out of the room yet. So right now what we're asking is just to ask all the points, okay, ask the whole lecture theater, okay, everyone, just go and measure how far you are away from the door. And it's saying that this is, let's just say this is the door, right? Okay, actually, let's say, let's get back the right and left probe. So actually, so let's copy paste it over here. We want to measure from the original one, not from the offset one, sorry, my bad. So we want to measure it towards here, right? Say, okay, everyone, how far are you away from this component here? And it will tell you, oh, this is the distance that I am away from that component for each of these points. So if we have 102 points, we're gonna have 102 distances, right? And because some of them are directly on the curve itself, you're gonna see that some of these have basically no distance away. It's a very small one, but it's not exactly zero, like 0.0 blah, blah, blah. So let's just pull out a numerical operator now. We say less than. If we say, let's say that if the distance, we just, okay, this, what this does, it compares two numbers. It compares whether it compares A and B. If A is less than B, then this one will give you true, right? So we say if distance is less than 1, because I remember this distance is not perfectly 0, we cannot say if it equals to 0, then please stand up. We'll say if you are less than 1 meter away from the circle, please stand up. So we just said that. Or if you want to be even more precise, and you know that it's very, very close, you can maybe say if you're less than 0.1 away from the circle, and which all of these are, then please stand up, right? Then now if we do cal point, we do cal index, cal pattern, right? So what cal pattern do is that, oh, you can do a dispatch actually. Dispatch might be better for this. So what it does is that it takes the input list and a pattern, and a pattern here, and it will dispatch them into group A and group B. Group A being true, group A being false. So pattern means a true or false pattern. If you look at the input symbol, it's asking for Boolean, and list is just asking for a generic list. So if I take list as in the number of all these points here and plug into here, and say, okay, now that I have this figure here to distinguish what is less than 0.1. So I say all the points that are less than 0.1 mm away from this curve, you call yourself a true point. So you tell me that you are true. If you are further away, you are more than 0.1 mm away, then you are false, right? So we take the output with this long list of true and false values, right? Long list of true and false values. You see some as true, right? We put them into the pattern that we want to distinguish them by. So now this is our first layer of sorting them into classroom A and classroom B, right? So we preview it, you can see all those in classroom A. Now we have a very nice selection of just all those here only. And all those in classroom B are everyone else, right? So let's do this. And now we have our first right probe, our first right probe's points, right? So we can put this into right probe first, right? And for these purposes, for this specific example also, it's good practice to graft the naked points first, so that this one we have all this with the correct like label. So okay, don't have to understand what it does exactly, Let's know that if you're doing this, if you're following along right now, you need to graft it, right? Then right now, we can take the group B, which is everyone else left in the classroom, which is all these fellas here. And we say, okay, let's do it again. So let's do it for the left probe this time. So we copy paste away this condition and we say, okay, all those who are close enough to the left probe right now, please stand up. But we no longer want to talk about the whole LP. We only want to talk about those left in the LP. So let's take everyone else left in the lecture theatre and put it back into the points that we're analyzing. And now you see we're only talking about these points, right? And if we make another dispatch component and we only organize from, disconnect everything so it doesn't get confusing. If we talk about only all those left in the lecture theatre, so we take from this component here, right? And we give it a pattern. So the pattern being all those that are close enough to the left probe that they are less than 0.1 mm away. And we dispatch it. And now we preview it again. You can see these are all the people that are close to the left probe. And this is everyone else left in the LP, right? So what we can do now, we just put this here and type say left probe points. So we can say right probe points. Right? And for the sake of understanding everything else, let's just turn off the preview of everything so we don't mess up our preview. We don't have too many things. Yeah. So now what we can do is we can pull the points over to this curve. Say the right probe, right? We need to pull it up to this point. You can either do a move component into there and move it up and down based on the translation vector. So if you want to do a translation vector, you say you want to move it in the z direction, create a z unit z component, which tells you want to create a z vector, and then you create a number slider that tells you how long this vector is going to be. So let's just say we create a slider of 10, and we plug the vector into the translation vector. Right now with this slider, we can start to move it up and down. So if we move it by 0, you're not going to move it all. If we move it in the z-axis by a factor of 10, you're going to move 10 times in the z-axis by, because this is a unit vector, so this is going to move it 10 mm. Because 10 times 1 is 10 mm, right? But if you want to move it precisely to this curve that is set up in Rhino, you have to do the next technique that I'm going to show you. This one is if you just want to experiment around and you just want to like say like, or like maybe say you know that this is going to be like 10 cm above. So 10 cm in mm is 100 mm. So just say that, oh, you're going to move it there, which, okay, 10 cm is this high lah. Maybe this is not exactly 10 cm, but if you're going to say 10 cm, then that's, you're going to move that up there. Right, so that's one way. Another way, you can use the pull command. So you can pull a point to a variety of geometry. So we take the point that we want to pull and we plug it into the point component. The geometry that pulls, we plug it into the component that we want it to pull towards. Right? So offside, we want it to pull towards this curve. So we set it to there. Then immediately you see the points will snap up to the curve. Right? And we can do the same for the left points. Just that now we take the left probe points, we put it into the point component, and the left probe, we put it into the geometry component. And you can see now it's these points will now snap down to this area down there. Right? Sorry. And now let's turn off this preview so we don't get confused again. And yeah, so we have these two set of points as well as everyone else who is left in the lecture theatre now, which are the boundary points, because that's everything that's left, right? So if we merge, so that we know these are our new targets to pull towards. So we can merge all these back into a single target. Since these are all the points that we're gonna anchor at, so let's just merge all of them together, to there, into there, and into there, right? And take this as the new targets. Remember just on the anchor component, we say targets. So this is the new targets that we want them to move towards. And if we reset the simulation and we turn on, you see now it's going to start to move towards there, right? And if we lower the factor, you can see how it starts to change. If let's not make it more than 1. So let's say 0.99, right? So now it's always going to be trying to be smaller than the original mesh, which is always going to give us the smallest mesh possible, right? So if we take this curve now and we try to move it there, and remember, every time you move something, you gotta reset the simulation. Oh shit, that's not the way. Oh, my bad. This is not exactly how you do it. It's kind of wrong. Okay, this is only if you, I think this is good practice only if you want to move it up and down, right? But okay, let me do this a bit more prudently. Sorry. Okay, so let's say we want this to move from here to here, right? So this is gonna be one. Okay, wait, let me undo everything back again. This is gonna be one way where it's the limitation to this method is that you can only translate it up and down. You cannot really twist it. As long as you start twisting it, it's gonna degrade a little bit, right? So you can move it up and down. You can push that and have this geometry, right? Let me teach you another way, which is maybe a bit more prudent in terms of setting up your original geometry. So let me set it there and say only move probes. Right, then let me disable this and unplug this so that we don't confuse the simulator anymore. Right, so let's turn this off. And now let's set up the simulation in a different way. So remember just now where we patch everything, right? We take this, we take this, we take this, and then we patch it all. And we have this shape, right? And we realize that, oh, it's not exactly correct. So that's one way that we can use to make it, to improve this shape and make it even better, right? So now instead of choosing left probe, instead of having all these here, we hide away the offset probes. If the left probe and the right probe, what we can do is, if originally because we're choosing planar mesh, a planar surface, so this will only create a surface on the planar boundary, right? But if we create a patch surface, we try and create this surface as much as I push it down or pull it up. Oh, that's weird. Why is it not? Yeah, as much as I pull it down or pull it up, or if I twist it here and there. Never mind. This is making a bit weird. How do I do this? Okay, never mind. Psych, turn this back on. I think this is better. Okay, so instead of using pool, sorry. I say guys. Okay, instead of using pool, right, let's use something else. So let me remove this from the group first. And let's figure out the translation vector from this probe to this probe, right? Because these are essentially the same. So if we set it up like this, say if I gonna twist it to be like something like this, and this one I'm gonna twist it to be something like this, right? Not so much maybe, and this one also not so much maybe. I want it to not just move down, but I want it to move to the side and also twist it, right? So what we can try and do is that one very primitive way of doing it is seeing all these probe points, right? And we know these probe points, they are, these ones are the right points, these ones are the left points, this one is the boundary points. You don't have to worry about boundary points, we have to worry about everything else. So we gotta give it a translation vector. So we're gonna move it from here to here, right? So we can try compare this curve to this curve. And we can do that using transform. And by transforming, we can use, where is it? Where is it? Orient. There we go. So what it does is just change it from from one plane to another plane, right? And so we want to offset the initial geometry. Oh, no, we don't offset the initial geometry. Let's just talk about it as from a plane to plane, right? So left probe is going to be one plane. So let's convert that into a plane. Just like plane. And because it's a planar curve, so it's very easy to give it into a plane. If you are doing curves of like different shapes and sizes, that one, uh, if you're gonna do that, come find me. I'll help you to work through that. But for this scenario, I don't think everyone's gonna try and do that lah. So I'm not gonna try and do that right now because there's a way to do it. You bounding box everything, and then you deconstruct your bounding box, and you change the plane of the bounding box instead by taking for example, if this probe is like weird shape and it's not flat, right? You bounding box it, and from bounding boxes, you create something that is planar, and from there you can work on it further. Right. So, but for now, we're simple because we have a plane. So let's just say left plane, and the right one, we create another one and say for the right plane. So if I select both, you can see now. Let me turn off this one as well, so easier for you to see. There's a left plane and a right plane, right? And let's copy paste this and move it down to here. We're talking about the left probe, the offset left probe and offset right probe. So let's create a new plane for the offset left plane, and create a new plane for the offset right plane. Right? And now if we look at the orient component, it's asking for the geometry to orient. It's asking for our initial plane, and it's asking for the final plane, right? So the offset plane is going to be our final plane. And our left plane here and here, this is going to be our initial planes. And the geometry that we want to offset, we're not going to offset the curve itself. We're going to offset these points, the probe points over here, right? So let's work with the right probe points first, and we take the right planes, move it here. And we take the right planes over here, and move it here as well, right? It's going to look messy, but it's fine. If you don't want so many wires going around your grasshopper, right click, wire display hidden, to turn off the wire for it, right? If not, just leave it on, it's fine as well. Or this is something I like. You can use this plugin called Telepathy. It will give you a remote receiver and a remote sender. So what it does is that if you give it a sender, this is like, it's basically you're giving it Wi-Fi. So you give it like left plane. So now, if you double click this, you create your receiver. So this is like your modem, and this is your PC. So you have a left plane, and even if you don't have a number here, right? If you disconnect this as well, if you right click this and click keys, you're gonna give you a list of all the things that you have. So for example, I have a right plane over here. If I right click this and click key, I can choose whether I want it to be left plane or right plane. If I say left plane, then it's gonna show me the left plane. If I click right plane, it's gonna show me the right plane. And this will act just as a wire as well. So you can use this for your components. But it keeps your grasshopper very clean because it's wireless, right? The component is called telepathy. This one. Telepathy. It's quite good. But yeah, okay, moving on. So we want to work with the right plane only. So left plane, let's move it down back here. So we take our initial plane, which is this right plane here, plug into initial. The offset one, which is our final plane, we set it into the final. And the geometry to orient, let's set it to our probe points because that's what we want to change. So we plug this into here. Now you can see it's going to be pushed up there at an angle. Previously, it would just pull it to wherever closest on the point, but now we're going to orient it correctly to the angle. And if we turn off all these previews, you see now our points are up there. And let's repeat it again for the left probe points. Initial plane being the left plane here, the final plane being this final plane down here, right? And now if you turn off all these previews, you can see our oriented geometry is now down there, right? So if you turn off these left probe and right probe points, these are now our final anchor points, right? And let's plug this back into uh, the merge component. So it's from here, plug into there, here, plug into there, and our boundary points, let's just leave it there because it's already plugged in. And we can turn off all these orange. And now from the merge component, we plug this back into the target. Delete this address, we don't need it. And if I reset this and I simulate it, now you see it's going to try and push it up towards there, right? So if I give it a bit more length, not? Okay, what? Okay, 0. Give me a second. Let me see why is it. Oh, oops. Let's clean this up real quick. There we go. Okay, after you merge it, you should put in a clean component. Because now you see, if I turn on the panel, you see there's a lot of like null components, which are not very good for our thing. So if we clean up null components, what it does, you use a clean tree, you just remove all these erroneous data points. So now we have a clean data list to work with. Right? So let's plug the clean tree into there instead. And yeah, now you'll go into there. So if we try to twist this, we now have a minimal surface according to wherever we twist it to, right? Like that. And even if, like we say, we want it to be half in, half out, if you make a bubble in real life, that's kind of how it's going to look like as well, right? We can reduce the edge length and everything to look more like it. So that's one way to create your bubble structure, or like a tentage kind of structure. You can create like that, and it looks like two light wells. Like if the sun is up here, it can shine down here. If the sun's up here, it shine down here, kind of thing. Yeah. So that's one way of creating these bubble structures. And to extract out the mesh again, you see here, there's a whole lot of everything. There's a mesh, there's one mesh up here that we want, and there's all these lines down here that we don't necessarily need to work with, right? What we can do, just create a mesh component like that, and just plug it in, and it turn red because it says failed to convert from line to mesh, but that's kind of good because it kind of like filters out all the lines for us. So we hover over here, you're gonna see all these null components because it failed to convert from a line to a mesh, and all these other null components as well. And similar to down here where we have a lot of null components, let's create another clean component, plug it in, and now everything's all cleaned up and nice and cool, right? You're gonna have a lot of empty lists now because we cleaned out all the nulls. But what you can do is remove empty branches from the tree. Usually it's going to be set to false. If you right click it, boolean true, now we clean out and it's just going to be that mesh. Right? It's going to be a very nice clean mesh. Another way, simple way, just flatten everything, then just clean it as per normal. And then you don't have to worry about turning this to true also. But yeah, and now you have a nice mesh for you to use. You turn everything off and we just turn only the last one on and we bake this. You can see now we have this mesh in Grasshopper, which is what we generated from here, here, and here, right? So this is just one method of creating this bubble structure. There's another way using gold mesh and soap film, which is a very direct way and it doesn't give you as much control anymore. Like right now, we can still set the length factor. We still set the length factor and everything. But if we use, for example, if I set a length factor to be like very, very tight and strength to be very, very high, I mean,
it starts to devolve into like this kind of thing. If you give it like make it like a loose cloth kind of thing, um, or if you give it more points or anything, let's say the length like that, you make it a more and more refined mesh. You start to see that set it, say this length factor, let's set it back down also. You see a lot more movement as it tries to simulate, but that's because we give it a lot more like a lot more points to simulate. But it's also going to take a lot more resources. Like you see, my whole thing is starting to lag quite badly now. I'm doing converges, and then we have a very smooth mesh that we can once again bake out. Right. So now is our new extremely smooth mesh because we have a lot more vertices this time. Right. But not good for my computer, so I'm going to give it less perks. Yeah. Okay. Another way, the simpler way, which will not let you adjust all these length factors and edges, just take the mesh, plug it into this component called soap film. So there's a pre-built-in like thing that allows you to simulate soap film, which is exactly this. Uh, and this component. So this component called live soap and soap film. If you just use soap film and plug it straight into goal object, it will not be very good. You still need to replace the edge length with it. It's gonna give you this. It's very messy, and you keep iterating until like you get something clean. Just pause it, but you can see it's not exactly the best lah. You can improve the meshing using the live soap component. So mesh goes to mesh. Use volume. Set it to false. Volume difference, just set it to false. So strength, you can just leave it. And the reset button, connect it to the reset button of the simulation, right? And this one, same thing, drag it into the goals as well. So now if you reset everything and let it solve, you see it gets a bit, I don't really like it, but it's what you have. Yes, yeah, it will devolve a lot, especially if these parts are very far away. Because what it tries to do is that you try like it's okay for if your things are close by, but if for example like I show you, it starts to get closer and closer, you try to simulate real soap in the sense that these parts here they start to join together a bit more, right? Like so you can start to see it starts like that and it will scoop its way up. But at the same time you can see that it degenerates the mesh quite a bit because of that. Yeah. Right. Because it tries to combine the vertices as well as it's doing that. So that's one way you can do it. It may not be the best way, but if you're doing things like that doesn't affect it, like for example like this, like it could create a nice mesh for you. So you don't have to worry too much about it. But if we ignore all that and go back to the original way, this is always gonna be the more prudent way to do it because it's a bit more control over everything. Right? It gives you a cleaner mesh at the end, like it gives you this nice mesh. Right? Yeah. Okay. I think I yapped too hard. It's been 3 hours. I'm so sorry. I thought this would take an hour and a half. Um, I hope it's not too confusing for y'all. Put this in here. Put this as well and say soap mesh. Right? And turn off this cover and I'll turn it off as well. Okay, good practice, right? Whenever you save your file, right, just turn all these solvers off so that when you reload the file, right, you don't get flashbang with like 5 different solvers trying to solve at the same time. So if you turn it off, when you load the file back, you're gonna start as off. So it won't try to like load everything while you're just trying to open a file and look at what you have, right? So yeah. Let me break this out. I think it's quite cool. And solids. Yeah. Okay. That's that's kind of all for this tutorial. I'm so sorry it took so long. I hope you all have learned something. If not, that'll be all for now. Feel free to ask questions in Telegram or anything, or text me or anything. Uh, yeah, I'll send all the files to the group, and I'll send the recording as well to the group. And yeah, okay. Rest while you can. I will see y'all on Monday. Yeah, that's all for now. Bye bye.
Thank you.
Yeah, I'll share the script also. Yeah, I'll send it to the Telegram chat. Okay.
Can okay. Bye bye. Thank you.